and then 2 minutes for the transition to the next speakers. Okay, so I think we can start now. The first speaker of today's this para session is Kang-Hoon Lee from APCTP, and he will talk about Valence-Gillet recursion relation for gravity and double copy. Please go ahead.
Yeah, thank you for introduction. So today I talk about my ongoing work with Kwang-Hoon Kim and so before start, I'd like to thank to the organizers for giving me a chance to talk. So yeah, this for the time limit, and this is not fully done, so I'll skip all the details and share the some brief idea of this project. So let me explain what is the Valence-Gillet recursion relation. Actually, this is for Yang-Mills theory. It starts from Yang-Mills theory, and it is actually we know that the computing scattering amplitude using the conventional method using Feynman diagram or Feynman rules is very tedious and involves a lot of computations. So it's well known that if we compute for example 10 particles in 3-level amplitude, we have to compute more than 10 million diagrams. So so it is impossible to use the conventional technique for that. So there were many attempts to construct efficient tool so this is one of the example, and the most well-known example is the BCFW recursion relation in 2004 something. And the basic idea is that we can recycle the pure lag regions. So if we compute 10 or more than that, then particle scattering amplitude, then we can use the results for 9, 8, 7 amplitude. So, and it turns out that this is very powerful technique. Before BCFW recursion relation, there was another recursion relation which is also very powerful, and it's constructed by Valence and Gill in 80s, and it's often called the off-shell recursion relation to be compared with the on-shell recursion relation in the BCFW one. So the reason for why it's called off-shell will be clear soon. So let's consider scattering amplitude for k+1 particles. So this is this bulb represents some diagram, Feynman diagram, and we assign we have to assign these k particles on-shell state, like so we have to add so impose some external momenta and polarization vector or color factors. But the last k+1 particle, we don't assign anything. So this is, it doesn't have, the k+1 momenta doesn't have to be to satisfy on-shell or mass shell conditions. So that's why we call it off-shell current. And the reason for we said that this is current because it said it is really conserved. But yeah, we don't have to assign. So usually when we track that conservation, we have to use equation of motion. But in this case, we don't have to use any equations of motion. It's more like word identity. So, but any so we can rearrange the Feynman diagram in this way. So if we consider k+1, then we pick up the last particle, which is off shell, and we assign the k particle in the way. But we can always decompose it like that. So because in Yang-Mills theory, there are two kinds of interaction vertices, 3-point and 4-point. So we can divide that always this way. So this is the equation for this diagram. So so this blob also always represents currents. So this first line represents this first diagram, and the next one, this one is represents as 4-point vortexes. So if we take a look at any of these current, there is same structure like that. So we can define recursion relation. So this V3 is a 3-point the vertex, and the V4 is the 4-point vertex. And so we have to assign the initial condition, and the way is that we have to assign the first one as a polarization vector. So it can be plus or minus helicity. And we can construct scattering amplitude by taking the onshore limit. So we have, so in order to get the conventional scattering amplitude, we have to couple with the external momenta and polarization vector for k+1 particle. And then we have to take the onshore limit for that case. And the reason for multiplying this k-square is obvious that, so if we remind the LSF formula, then we have to use amplitude Feynman diagrams. So in order to cut the propagator or cancel the pole, we have to multiply this one. And then this really gives us scattering amplitude, or it should be a color ordered amplitude, but I'll skip that part. So this is very powerful as well, and many amplitudes obtained by this way. So was very successful, but we can ask that whether we can find a similar thing for gravity rather than Yang-Mills theory. So compared to BCFW, so BCFW is perfectly fine. So BCFW requires a specific condition for working. So and if we have a large momentum case, it should drop. It should be going to zero very fast. That's the requirement. And gravity satisfies the condition very well, so there's no problem for applying BCFW recursion relation for gravity. But how about Brans-Gill recursion relation? So it is clear that it's impossible in this conventional way using Feynman vertices, because perturbative gravity is very complicated. And as you know, there are infinite many irregular interaction vertices appears there. So you cannot control them. So you cannot write down in this way. So there are infinitely many vertices, so we cannot have a proper recursion relation from this. So, but it's worth to check that what's the source of this complexity for gravity. So if we do this linearized perturbation, then the inverse metric and the square root of determinant of G gives us an infinite order of expansion. So that's the main source of this complexity or complicated expansion. I'd like to ask to is really hopeless or not? Of course, if it's really hopeless, then I have to stop my talk in here. But I'd like to emphasize there are two very good ingredients for constructing this recursion relation. The first one is double field theory, and other thing is a part of inner expansion. I will explain both of them now. So the double field theory is the closed string effective field theory. So basically, this is gravity, supergravity, and we have an additional structure, ODD duality covariance. So the direct consequence of this ODD covariance is that we have to double the space-time dimension. It does not mean that we are in the double space-time, but we have to add additional constraint to halve the degrees freedom. That's called the section condition. And this idea is quite a long history. So there are two directions for this, and the first one is schema model, and then it started from 90s, and also there is another approach is the low energy effective field theory side. So it's rewriting the basically supergravity. So the consequence of this is that we can geometrize all the bosonic fields in NSN property in curvatures. So the action and equation motion can be written in terms of the generalized version of curvatures. So let me tell you that the DFT field content. So the manifest T-duality means that we have to use all the ODD tensors. I mean, it transforms as a tensor under the ODD transformation. So there are two fields. First one is generalized metric. It's linked to symmetric ODD tensor, and as well as this ODD element. So yeah, it's different things, ODD tensor and ODD element. ODD element means that it satisfies this relation where J is the ODD metric. If we do the diagonalization, it really becomes 1 minus 1. But here we are dealing with the off-diagonal representation. And then we can solve this equation explicitly. Then we can make a connect with the NSNS sporography field. So can be written in terms of G and B field. And another ingredient is DFT scalar fields. So it involves scalar G in there. So it plays a role as a measure. So one important thing is that when we define inner product in the generalized tangent space in 2D dimensional space, then the H is not the metric. It does not define inner product, but J is the metric. I mean, gives the inner product. So we can use the ODD metric to raise or lower the ODD indexes. And so it is important. And inverse of H is itself. Because H is element of ODD, so it has constant determinant, so orthogonal group element. So we don't have to worry about the inverse or determinant of H. So if you remind that the source of complexity is the inverse or square root of the metric, it is free. In DFT, this problem is not the problem for this case. And Lagrangian is written this way, so there's no problem for that. So one may ask that is this really gives a finite expansion of gravity or not? So actually, it is hidden in the side H. So we have still infinite expansion of the perturbation, but it's hidden inside H. So for simplicity, let's consider pure gravity case, turning off all the
Yeah,
B.
3-minute warning.
Okay, thanks. And phi equals 0. And perturb the generalized metric around the flat background. This is a fluctuation. And then we can always decompose into the 4 different sectors. And so this is because we can introduce chirality operators. So this E and E bar are the mixed chirality part, and delta bar are these chiral and anti-chiral sector. But we can show that E and E bar are linear perturbation, and these chiral anti-chiral sectors can be written in terms of E and E bar. So delta gives us the infinite order expansion like that. And for pure gravity case, the fluctuations are related by that. So E is just symmetric, and the E bar is identical. So we can use this expansion for that. The other ingredient is perturbina, and one may usually ask that the tree-level scattering amplitude is unusual, and the solution it should be related to the solution of diffusion motion, but it's not clear. But the perturbina expansion is so-called perturbina expansion connects these two things together. And this is the perturbina expansion. Actually, it's a multi-particle expansion of the plane wave basis. And here P is the words and IJ is letters, and P is labeling the multi-particle indexes, and the IJ is particle number. And interestingly, these coefficients, it turns out to be the Behrens-Gillet currents. So it's a kind of generating function of Behrens-Gillet off-shell currents. And then the recursion relation can be obtained by substituting these fields into the equation of motion. So this is another way of obtaining the part. So yeah, so we can combine these together, and we can define the perturbation expansion for the generalized metric. And then if we substitute that into the equation, DFT equations motion, then we can get the Behrens-Gillet recursion relation. Is not using any Feynman vertices. So and then the one interesting stuff is that the double copy is encoded in double field theory. And then, yeah, I'll skip this part, but the point is that so we can see the double copy structure. Double copy is that just the gravity amplitude can be obtained by Yang-Mills scattering amplitude in that way. And yeah, it's just some current version of double copy relation. And combining spino-helicity formalism in scattering amplitude, we can ignore the gauge transformation part. So it's my basic motivation that so that seeing the double copy structure in equation motion level, and this is it shows that the statement. Okay. Thank you.
Okay, thank you very much. Thank you for an interesting talk. So we have a few minutes for the questions. If you have a question, please turn on your microphone and ask questions.
So can I ask a question?
Sure.
Sure,
Yeah.
yeah.
So what I understood is that if you write things in double fields, H, the infinite order expansion and infinitely many vertices seem to disappear. That's one of your points.
Sorry, my internet connection was not good.
So the Yang-Mills theory has just two vertices, while the gravity seems to have infinitely many vertices.
Yes, right.
It seems that you go around it by using the double field H, because the non. So
right.
you mean that problem can be cured by careful field redefinition even in pure gravity?
Yeah, so we can connect the metric perturbation and the generalized metric perturbation, and this is related to very complicated way. It's very non-trivial. So usually gravity perturbation cannot see the double copy structure, for example, but here perturbation of generalized metric, the
No,
structure is
I didn't mean the double copy structure, but infinitely many vertex or versus finitely many.
So even DFT has infinitely many vertices, but the problem, it can be cured by this perturbation expansion. So we don't have to use the Feynman vertices, but you can use equation motion directly. And yeah, the infinite order expansion can be hidden in the delta on the field. And then, yeah, we have, delta field. We can treat the delta and the E as independent fields, and we can, as an auxiliary field delta. And
so this Portabino technique is independent of double field structure?
it's another one.
To do it?
Okay. Yeah, we can use the technique for Yang-Mills case as well.
Okay. So when can Portabino technique be applied? I mean, when is it not applicable?
I don't see any trouble for applying this technique for other theory, like scalar 5-fold theory can be applied there, or any vector theory can be applied there. I mean,
okay.
Yeah, it's quite universal technique.
Okay, thank you. Okay.
So is there any other questions? So we are a little bit behind the schedule. Okay, if not, let's thanks Kang-Hoon again. Thanks for the very good talk.
Thank you.
So the next speaker is Johannes. Johannes, can you turn on your slide and see whether it works?
Yes.
Okay. So
okay, do you hear me?
Okay, so are you ready?
Yes.
Okay, so then the next speaker is Ioannis Papadimitriou, and from Kias, and he will talk about anomalies and supersymmetries. Okay, go ahead.
Okay, thank you, Sung Sung, and also the organizers for the invitation to present this work here. So the problem I'm going to discuss is related to continuous global symmetries that are anomalous. So example of this are like flavor symmetries or R symmetries, but they can be also other symmetries like higher form symmetries, for example. And in particular, I want to discuss what happens to these symmetries in the presence of supersymmetry. So how the two interact. And the main idea is that this continuous symmetries, they give rise to some conserved current via the Nether procedure. And in the presence of supersymmetry, this gets enhanced to a multiplet. So that can be either a vector multiplet or a gravity multiplet. And I would like to distinguish two different types of multiplets. So what I call like a small multiplet and a large multiplet. So the small multiplet can be thought of as, so typical examples would be n equal 1 vector multiplet in 4 dimensions in the West-Zumino gate. And a typical large multiplet, it would be the same multiplet, but in superspace. So they differ by auxiliary fields that that play an important role. But in many examples, it is not possible to have this large multiplet. So an example of that is the conformal multiplet, for example, the conformal gravity multiplet in 4 dimensions, or the R multiplet, and several extended supersymmetry cases. So in that case, we don't have the analog of superspace, so there is no large multiplet analog for such cases. So, and what I'm going to discuss is what happens for this kind of multiplets where this continuous symmetry is anomalous. And as I will explain, in this case, there is a deformation of the supercharged algebra. And like the consequences of that are multiple, especially like in the case of supersymmetric observables on curved backgrounds. So for example, one of the main consequences is the non-holomorphicity of refined supersymmetric observables. I will try to discuss this towards the end a little bit more. And also the supersymmetric Casimir energy is affected by this deformation, as is the BPS relation from conserved charges. And in particular, this makes it very important, like to be careful, like to take this effect into account when we compare supersymmetric observables computed in different ways, for example, via localizations and hologram. So there are several references that pertain to this talk. So I will mostly talk about this last paper here that appeared like a couple of months ago, but also a series of earlier papers that this paper built on. And there are several other papers in recent years that discuss very closely related phenomena. So this is the plan of my talk. So I'm going to set the stage by reviewing some very basic ingredients that we will need later on. And then I'm going to discuss supersymmetries, in particular the world density and the anomalies that appear. And I will discuss supersymmetric anomaly inflow and what consequences this phenomenon has, like in partition functions, supersymmetric partition functions. Okay, so first of all, again, just as I said earlier, so the basic principle is that, at least at the classical level, when we have a continuous global symmetry, we know from Noether's theorem that there is a conserved current. So this is reflected in this equation here. And it also leads to a conserved charge. So if we integrate the time component of this current along a constant time slice, we end up like with a conserved charge. And in principle, we can have multiple charges, and they satisfy some algebra here. So they would be generically fermionic and bosonic charges. That's why I put like these mixed brackets here. But in general, there is some closed algebra that these charges satisfy. Now, at the quantum level, this story is modified because of anomalies, and this is exactly what I want to discuss. So, a very systematic way of analyzing both conserved currents and their anomalies at the quantum level is introducing what is known as background fields. So, in particular, in this case, this amounts to turning on like a Gates field, a background Gates field A that couples to the Noether current, to the conserved Noether current J. So this is how this effective, so then the path integral over the elementary fields gives like an effective action that depends on this background field. And this can also be thought as a generating function for correlation functions of Noether currents. So if we take successive derivatives of this effective action with respect to the background Gates field, we compute like the endpoint function of Noether currents. Now, what are anomalies in this context? So these are like simply the statement that this effective action is not Gates invariant under a Gates transformation of the background field. So in the infinitesimal version, this takes this form here. So an infinitesimal Gates transformation is non-zero. So this is known as the integrated consistent anomaly, and there is a local version of that. So, and this observation here gives rise to the non-conservation of the current. So if we compute this variation in two different ways, so the first here being just the chain rule. So I just use the definition of the current here and the Gates transformation, and also here this anomaly. So if we just now use the fact that theta is arbitrary, we end up like with this non-conservation, anomalous conservation of the current. Okay, so now how do we determine this anomaly here? so this anomaly has to satisfy what is known as the Wess-Zumino consistency conditions, so which states that like two successive gauge transformations, they have to close like on the algebra. So in particular, like this is the expression here at the level of this effective action, or in terms of the anomaly is this equation here. And solutions of these conditions are non-trivial local functional G of both the gauge parameter and the gauge field that are not variations themselves of some other local function of A. So in that sense, this is a cohomological problem and can be solved using some BRST formulation of the algebra using what is known as anomaly descent. And the final ingredient, like I want to introduce, like I mean, which is should be familiar, like to most in the audience, is what is known as the Bardeen-Zumino polynomial. So the observation, this Bardeen-Zumino polynomial is based on the observation that this consistent current that we defined earlier is not covariant under gauge transformation. So in particular, you can compute its gauge transformation, and you find that there is this covariant term here, but also due to the anomaly, there is this inhomogeneous term here as well. Now, Bardeen and Zumino, long time ago, observed that actually there is another local polynomial of the background fields. So this is the Bardeen-Zumino polynomial. I'm not writing explicitly now because it depends on the dimension. But it takes this form here. So it transforms in the same form, but with opposite sign here for the non-homogeneous piece. So if you combine the two, you end up with a current, the so-called covariant current that has a homogeneous transformation. So I just mentioned this because, as we will see in the moment, this Bardeen-Zumino polynomial plays a key role. So now let's go to supersymmetry. So in the case of supersymmetry now, in the presence of this of an anomalous flavor symmetry, we have additional Wess-Zumino conditions. So there are additional transformations to consider. So in particular, there is this mixed Wess-Zumino condition here, which implies that there is a non-invariance of this effective action here under supersymmetry. So just because the supersymmetry variation of this anomaly is not zero, so it depends generically like on this Bardeen-Zumino polynomial, which we just introduced. And this implies that the general variation, the supersymmetry variation of the effective action takes this universal form. So there is a universal piece that depends on the Bardeen-Zumino polynomial, plus a gauge invariant term here that depends on the specific multiplet and is determined by the mix, the supersymmetry Wess-Zumino condition. So as a result of this, now we can write down the word identity for supersymmetry, and it takes this universal form. So there is this is the supercurrent, and there is also here. So this term here combines like into this covariant current, like for the flavor symmetry, and then there are gauge invariant terms here on the right-hand side. So this form is universal, but first, let me just do an explicit example to see more familiarly, like I mean, how it looks like. So for example, like in the simplest possible case, like in 4-dimensional n=1 vector multiplet, this is the usual, like the usual U1 anomaly. But now we have a multiplet of background fields and corresponding operators defined in the standard way. And also a bunch of Wess-Zumino conditions to satisfy. And long time ago, Itoyama, Nair-Ren, and Guadagnini and Mitchev, they actually found the general solution of these Wess-Zumino conditions for this particular case. And well, the gauge variation takes the standard anomaly expression, but there is also a contribution from the supersymmetry variation that takes the standard form that we just saw. So here is the Bardeen-Zumino current for this particular case, and then this is a gauge invariant term that depends only on the gauging. And this is the corresponding word identity here, like because now there are additional operators in the multiplet, there are other terms here, like for example, this term. But here the important thing is that there is the covariant current appearing here. So as I said, the punchline is that this expression here for the variation of the supersymmetry variation of the effective action is generic, and it actually generalizes to local supersymmetry. So it applies not only to all vector multiplets like in even dimensions, but also current multiplets. So for example, the conformal current multiplet in 4 dimensions, and also the R multiplet and but not, for example, in the Ferrara-Zumino. So the Ferrara-Zumino is an example of the large multiplet. Now, the non-invariance, so this expression here can be determined, so, well, this part we know universally, but this expression here can be determined systematically, either through a generalized version of anomaly descent that we discussed in the paper with Pilzingi and Ruben Minassian, but also through anomaly inflow. So a supersymmetric version of anomaly inflow. So let me just give you an example of this. So remember that anomaly inflow essentially amounts to, in the standard bosonic anomalies, so it amounts to the statement that the anomalies, the consistent anomaly, are in one-to-one correspondence with the Chern-Simons form in one dimension higher. So this is the Chern-Simons form that is given by the anomaly polynomial here. And the statement is that this Chern-Simons form cancels the anomaly through inflow. So the statement being just this expression here. So if you take the gauge variation of this combined expression here is 0. So the question is now, does this generalize to supersymmetric cases? And the answer is it depends. So it depends on the particular multiplet. And if there is if there exists like a supersymmetric Chern-Simons action, then indeed this is the case. So in particular, the supersymmetry and the gauge variation of these Chern-Simons produces the corresponding anomalies like for of the effective action. So a concrete example of that is in 2 dimensions, for example, the PQ flavor anomalies with P and Q less or equal to 3. So, and this can be determined by using the n equal 3 Chern-Simons that was originally found in this paper in 95. So you can just compute the variation of these Chern-Simons, and what you find is precisely these 2 anomaly terms. So this is the standard gauge anomaly, and here is the supersymmetric completion that is obtained from the variation of the Chern-Simon term. Okay, so now let's look at the consequences of this non-invariance of the supersymmetric partition of the supersymmetric effective action. So the question is what is the consequence of when this expression is not 0? So when the supersymmetry variation of the effective action is not 0, and to figure out the answer, we can actually look at the variation of the fermionic operators in the multiplet. And for example, for the vector multiplet, there is this operator dual to the gauge zeno, to the background gauge zeno field. So if we compute the supersymmetry variation, we get a homogeneous term here that gives like the conserved nether current. So again, these last expressions here are very schematic. I drop all the indices and there are gamma matrices and so on. But like the point is that there is a homogeneous term proportional to the nether current, to the flavor nether current. But there is also this non-inhomogeneous term here that is determined by the anomaly. In fact, is the derivative, the gauge zeno derivative of the anomaly. And similarly, there's an analogous expression for the gravity multiplet or the current multiplet. In this case, the relevant fermionic operator is the supercurrent. And then again, we have a homogeneous term here that is determined by the stress tensor and the R symmetry current. And there is an inhomogeneous term that is given by the gravitino derivative of the anomaly. Sorry, right. So this means that in particular that now if you put this expression here to the left-hand side, we see that these expressions here, these bosonic operators here are not Q exact. So the usual naive argument of the supersymmetry algebra would be that these operators are Q exact because they can be written in this form as the Q variation of some other fermionic operator. However, these anomalies here violate this Q exactness of these bosonic currents. So how does this affect the partition functions or other supersymmetric observables? So the point is that the naive supersymmetry algebra generically leads to these partition functions naively being holomorphic in certain fugacities. So schematically here, I indicate by tau generic like geometric fugacities, and by nu here some flavor fugacities. And now the holomorphicity is violated when by the fact that these operators here, these currents, are not Q exact as we just saw. So in particular, if we take the tau bar derivative of the partition function, then we find that it brings down this operator here. And because it's not Q exact, we see that like there's a non-trivial contribution coming from this expression here from the anomaly. So this can be non-zero even on a background that is purely bosonic, like it has like non-zero bosonic fugacities, because this anomaly is linear in the gravitino in the fermionic background, and here we have a derivative with respect to the gravitino. And similarly, the same applies like to flavors. So when we take the variation, the derivative with respect to the new bar, like so that's a flavor fugacity again, we bring down the flavor current, and then the same thing happens. So we saw that this is not Q exact again due to the anomaly as well. So that's the main consequence, and as a result, like these anomalies break the holomorphicity of the partition function. So let me summarize. So first of all, we saw that there is a generic expression for the supersymmetry variation of the effective action in supersymmetric theories with an anomalous global symmetry. So in particular, there is a universal piece that is determined by the Bardian-Zumino current, and the gauge invariant piece that depends on the multiplet and can be determined either by, so generically, all terms are determined by the Wess-Zumino conditions, but this can be solved systematically either by some generalized anomaly descent procedure or through supersymmetric or via supersymmetric Chern-Simons form whenever this is possible, whenever the multiplet admits one. And the consequence of this observation here is that the fermionic components of these global symmetry anomalies deform the supercharged algebra. And as a consequence, this affects the dependence of the supersymmetric observables, like refined supersymmetric observables with a flavor on geometric fugacities on these fugacities. Thank you.
Thank you for the good talk. So we have a few minutes for questions. So if you have a question, please turn on the microphone and ask questions. I guess, yeah, we are a little bit behind the schedule. Maybe we can close this session, close this talk. Okay, so let's thank Ioannis again. Okay, so the next speaker is Jonggi Yoon. Can you? Yes, sure, you can.
Yeah, probably. I hope you can see. Can you see the slide?
Yes, we can see the slide. Okay, so
And can I
you
start
ready?
now? Yeah,
Okay,
I'm ready.
So, yeah, okay. So the next speaker is Jonggi Yoon from TIAS, and he will talk about T-bar deformed fermionic theories revisited. Yeah, please.
Yeah. Hi, thank you for opportunity to present our work in the PASCOS. Today, I will present our recent paper, the T-bar deformed fermionic theory revisited. For this work, I collaborate with Pilchin Lee in TIAS and Kyung-Sun Lee in Drift. In this paper, we investigate various aspects of T-bar deformation. We work out the Hamiltonian analysis of T-bar deformation for the scalar field and free fermion. And we explore the relation between the T-bar deformation and various string actions. In particular, we study the T-bar deformation of free n equal 1,1 supersymmetric model and its relation to the Green-Schwarz action. We also study the emergent negative norm state in some T-bar deformation and the issue of non-unitarity. Today, we will focus on the TT-bar deformation of free n equal 1,1 supersymmetric model. The TT-bar deformation is irrelevant to deformation of two-dimensional quantum field theory by determinant of the energy moment tensor. Unlike general irrelevant to deformation, the TT-bar deformation follow the very special flow from the IR to UV, and this gives us two important properties. First, the spectrum along the deformation is exactly determined by universal formula here in terms of undeformed spectrum. This formula is universal, and this formula holds for TT-bar deformation of any quantum two-dimensional quantum field theory. The other property is that along the deformation, no extra degree of freedom emerges, unlike a usual irrelevant deformation. Usually, on irrelevant deformation, you can see that some new degree of freedom in the UV can appear along the deformation. However, when we construct some deformed Lagrangian, we found that the deformed system can have some emergent degree of freedom, depending on the type of energy moment tensor that we used. Namely, it depends on whether we use energy moment tensor from the Noether procedure or metric variation, or some other improved energy moment tensor. But this does not mean that TT-bar deformation can be coupled to the new degree of freedom, but it just means that there is some correct definition of energy moment tensor which does not give some extra degree of freedom. The example in our paper tells us that the energy moment tensor from the Noether procedure usually, not always, leads to the expected properties. But this is not true in general. Yeah, the example is the TT-bar deformation of the gauge theory. Now let's consider TT-bar deformation of n equal 1,1 Suji model. You can ask whether the n equal 1,1 supersymmetry is broken or not by this TT-bar deformation. As you see here, the deformation is not at all. So you may guess that the supersymmetry would not be broken. I mean, you might say that the supersymmetry might be broken.
Your slide seems to be not showing correctly.
Hope it okay. I don't know. Suddenly today it happened, but let me continue. Yeah.
We don't see any
based on the
slide.
deformation operator, you might guess that the supersymmetry is broken. However, the formula, if you see the universal formula for the deformed spectrum, does not care whether state is bosonic or fermionic. Whether it's bosonic or fermionic, they follow the same this formula, and this means that the Bose-Fermi degeneracy of the undeformed theory will be preserved along the deformation, and because the degeneracy is preserved, this means that the supersymmetry will be preserved.
Jeong-gi, I don't think
Although
we see your
supersymmetry
slide
is
at all.
preserved, it is not still clear whether the deformed supercharge has some local expression. This is something set independent problem. And in addition, the supersymmetric transformation is also
Jeong-gi, can you?
Yeah.
I think two slide has been not showing.
Yeah.
We don't see your slide. Can you adjust a little bit more?
Yeah, so
Junggi, can you hear me?
supersymmetric transformation is also deformed, and usually it is very difficult to show that the supersymmetry of the deformed theory is valid. Like the deformed theory has supersymmetry or not is also a very difficult problem.
Junggi, can you hear me? We don't see.
Oh. There.
So can you unshare and share again? Probably this will be better.
Can you?
Now we see
my
your
slide,
desktop screen. We only see your desktop screen.
Can you? I cannot hear.
Okay, so we can see. We can see.
Somehow.
Junggi, can you hear me?
Can you hear?
I can hear you. Can you hear me? Can you hear us?
Yeah, now I can hear. Yeah.
Okay, so I think it's now working. Okay, please go ahead. Yeah.
Yeah, sorry about that. Yeah, where can I start? I mean, I heard this slide
I think it's
was not shown.
page 9 or 12, 10.
From here or?
Yeah, I think from there. Yeah.
Okay.
Okay, next page.
Yeah, I'm really sorry. I don't know what happened. So, let me see. Yeah, it depends on whether you're using whether you use the energy moment tensor from the Noether procedure or metric variation or any other improved energy moment tensor. And it does not mean that the TT4 deformation can be coupled to the new degree of freedom, but this just means that there is exact correct choice of the energy moment tensor, which does not give the extra degree of freedom. The example in our paper tells us that the energy moment tensor from the Noether procedure usually leads to the expected properties. But this would not be true in general. For example, the TT-bar deformation of gauge theory is such an example. Now let's consider the TT-bar deformation of free n equal 1, 1 Suji model. You can ask whether the n equal 1, 1 supersymmetry is broken or not by TT-bar deformation. Since this TT-bar deformation is not supersymmetric, you might say that it breaks the supersymmetry. However, the formula for the deformed spectrum does not care whether state is bosonic or fermionic. Therefore, the Bose-Fermi degeneracy of the undeformed theory will be preserved along the TT-bar deformation. And this means that the supersymmetry will be preserved along the TT-bar deformation. Although supersymmetry is preserved, it is still not clear whether the deformed supercharge has local expression. In addition, the supersymmetry transformation is also deformed, and it is very difficult to show the supersymmetry of deformed theory explicitly. And you may wonder whether supersymmetry generalization of TT-bar deformation is possible or not. Yes, it is possible. There exists a supersymmetric TT-bar deformation by the superfield, which includes the energy moment tensor. However, the non-supersymmetric TT-bar deformation also has some emergent extra degree of freedom, which has some negative norm. So I will not discuss this model today. So now let's focus on the procedure. So let's begin with the Lagrangian of the free n equal 1, 1 supersymmetric model. One can solve this flow equation of Titeva deformation. And here, the energy moment tensor on the right-hand side of this flow equation is evaluated from the Noether procedure, not the metric variation. Now we will go to the Hamiltonian by calculating conjugate momentum of scalar field and fermion by varying the Lagrangian with respect to the time derivative. Time derivative of fermion appear linearly in the free fermion Lagrangian. And the variation with respect to the psi dot give us the relation between the phase space variable. It's very different from the scalar field. And this form the second class constraint. And you can calculate the Dirac bracket of this second class constraint. And this Dirac bracket will give us the usual anti-commutation relation of fermions. The Titeva deformation of n equal 1, 1 supersymmetric model has the same structure. It's just complicated, but the procedure is the same. And for example, the variation of the Lagrangian with respect to the psi dot give us the deformed second class constraint. And from this constraint, you can calculate the deformed Dirac bracket. It's very complicated, so it's difficult to calculate, but you can do that in principle, and we did. And with this deformed Dirac bracket, we could find two supercharges, which commute the Hamiltonian and the momentum operator. This is the expression. And this looks very similar to the supercharge of the just free theory. However, the conjugate momentum pi of the scalar field is different from the psi dot because of the deformation. The relation between them are quite different, as you see here. Also, you can see that we could see that the Hamiltonian and momentum can be expressed in terms of the supercharges. And this proves that the deformed theory is supersymmetric in all order in the deformation parameter lambda. In addition to the supercharge, this model has additional bosonic and fermionic global symmetry, which shifts the scalar field and fermion by constant. There, can you see?
We can see. We can see your slide, but we don't see you.
Okay. And can you hear my voice?
Yes.
Okay. Can I go ahead first? And then,
Okay.
is it okay? Yeah.
Yes.
Okay. Let's see. Okay. We also obtained those global charges under the Titeva deformation, and we calculate the deformed algebra. And together with n equal 1, 1 supersymmetry, we have deformed algebra of fermionic charges. It turned out that the Titeva deformation is related to the string action. In particular, Titeva deformation of a free n equal 1, 1 supersymmetric model is equal to the particular sector of n equal 2 Green-Schwarz action for 3D target space. Because
I think, Youngi, I'm sorry, your slide is not moving. Probably, can you unshare and share again?
Okay, I'm really sorry. I don't know what happened. Okay, is it okay?
Yes, so we are now seeing
Can you
Green-Schwarz action, yes.
Okay. And let me go dictionary. And can you see the next slide?
Yes,
Yeah,
yes.
okay, I hope. Okay. So I think I run out of time, so I cannot explain the details, but I would like to present some dictionary between the TT-body deformation theory and the Green-Schwarz. Here, the deformation parameter lambda appear in the definition of the so-called shifted light cone coordinate and the target space metric. And we choose the light cone gauge so that x plus is identified with worship time t. And the third component, the x2 of target space, corresponds to the scalar field in the TT-body formation. Also, after kappa symmetry is fixed, the remaining component of the spinner now become the fermion in the TT-body formation. And since the worship time is identified with the x plus, the charge for the translation of the x plus now become the Hamiltonian of the TT-body formation. Furthermore, we consider the discrete light cone quantization so that the x minus is now compactified. And you can consider the topological charge for this winding mode of the compactified x minus. And it is related to the momentum in the momentum operator in the TT-body formation by level matching condition. Now, we can consider the n equal 2 supersymmetric algebra of 3D target space from the Green-Schwarz action for the 3D targets. First of all, because of the Westman-Witten model in the Green-Schwarz, the supersymmetric algebra is extended by topological charge. In here, I cannot using my pointer. I worry about the error. So you can see that this A in the algebra is topological extension. And we show that this is exactly the same as what we obtained in the TT-body formation. Here, Q1 in the 3D supersymmetry, it is now become the n equal 1,1 supercharges in TT-body formation. And this Q2 of the 3D corresponds to the fermionic global charge that we obtain in the TT-body formation. And as I mentioned, the translation charge of x plus corresponds to the Hamiltonian because of time, and the correspond time of the TT-body formation. Also, this x2 become the scalar field in the TT-body formation. Therefore, the translation along the x2 become the now global charge which shifts to the scalar field that I also mentioned in some global symmetry in the TT-body formation. Also, the momentum in the TT-body formation appear in the Green-Schwarz as a topological charge of x minus winding mode. And when this x2, the target space x2 or equivalent is the scalar field in the TT-body formation is compactified, then we will have additional topological charge related to some winding mode of the winding mode. So we call it W2, and that also appear in this as a part of the topological extension. And because of that, this is exactly the same algebra that we found from the Dirac bracket.
I think you have a 1 minute.
Let me give, okay, yeah, I will level. This is final slides. And let me give them some comments on this result. Because of the Westmiller term and the compactified this x minus, a part of the n equal 2 supersymmetry correspond to the x2, and corresponding to this Q2 is broken. So in the literature, this is called the partially broken rigid supersymmetry, and this is known in the Green-Schwarz. And this is why we don't consider the fermionic global charge as a supersymmetric charge in the TT-body formation. Although it originated from the supersymmetry in 3D, but it's not the supersymmetry in the TT-body formation. Also, one can consider BPS state from the point of view of the n equal 2 supersymmetry of the Green-Schwarz. And we could see that those BPS state is protected along the TT-body deformation. Thank you for your attention.
Thank you very much for the good talk, although there's technical difficulties. So as we are very behind the schedule, let's have just one question from audience. Ioannis, you have questions? Ioannis?
No, sorry, it was a mistake. No, I don't have a question.
Okay. So then, as we are far behind the schedule, let's thank Jeonggi again.
Thank you.
The next speaker is Marcus Sperling is here. Can you turn on your slide?
You should see slides now.
Okay,
see them?
Very good. Okay, good. So next speaker is Marcus Sperling from Yao Center, Tsinghua University, and he will talk about the quantum curve for 60 and equal 1,0 theories. Okay, take it away.
Thank you very much. Thank you very much for the organizers for inviting me and giving me this opportunity here. I would like to use today's talk to report on some series of works that we've been recently working on together with my colleagues from Tsinghua, that's Baba Kagigat and Jin Chen, and also with Hee-Chul Kim from Pohang. And recently we collaborated with Xin Wang and Kim Young Lee from KIAS. And the topic today, as the title already says, is about quantum curves. And the first question is probably, what the heck is a quantum curve? And the answer is surprisingly simple if you just remember quantum mechanics. So the starting point is a classical curve. So that's an object that takes two variables. Then we just define the curve by defining a hypersurface. And here we can live in either the complex plane or the C star. And now since we have two variables, we can just proceed as in a normal quantization. We can say, okay, I can define a two form, and this two form allows me to define a commutator between operators that I promote my commuting variables to. And then this commutator, of course, is proportional to what we can consider as a Planck constant. And now if we just proceed with this prescription to the curve, then we just replace the algebraic condition with an operator equation. Now the operator is essentially everything that you do to the curve, and now the operator is acting on something, and that something is what is called then the eigenvalue or the eigenfunction. And if you remember your four-dimensional n=2 physics, then you will remember there's a curve that precisely fits into this framework, which is the Seiberg-Witten curve. So if we suppose that we start with a Seiberg-Witten curve, we can ask, what is a natural way of quantizing a Seiberg-Witten curve, and how do we interpret this wave function in terms of a physical quantity? And this is precisely the setup that we like to address. And the setup, or the starting point, is the 60 SCFTs, so the maximal dimension for these CFTs. And we can utilize the F-theory description, for instance. Here I give the example of a non-compact elliptic Calabi-Yau, which is composed of a chain of -2 curves, and each of them supports an SUK gauge algebra that tells you that the fiber degenerates in a certain Kodaira type. Similarly, or fully equivalently, you can use the dual M-theory picture that tells you have M five branes that have a 6-dimensional world volume, and I can choose to be along a torus times a remaining 4-dimensional real space. And these 5 branes, they are transfers to an A-type singularity. That gives you the equivalent setup. And now if we remember how to relate the conventional Seiberg-Witten curve to the geometry of Calabi-Yau spaces, then we know that the mirror Calabi-Yau has been shown to be the cone over a certain Riemann surface, and that Riemann surface is precisely defined by the 6-dimensional version of the Seiberg-Witten curve. So we start again having a curve in 2 variables, but now one of the variables actually promoted to be the exponential of that variable. So we have a C star variable t, and then the Seiberg-Witten curve is a polynomial of finite degree in this variable, and then the remaining coefficient functions depend on the other variable, which I call x. But now, unless in 4 dimensions where they could be rational functions, here they become meromorphic Jacobi forms in an elliptic parameter, which we call x. Hence, the Seiberg-Witten curve is now a hypersurface in T2 times the complex plane, and that's precisely the 60 version of the Seiberg-Witten curve that we would like to quantize. And this quantization now proceeds as already outlined in the first slide. We make the variables non-commuting, but we have already seen that we have to introduce an exponentiated variable. So the exponentiated variable is going to lead to a shift operator acting on the defect variable x. And then the corresponding quantum curve is in the realm of what's called elliptic quantum curve, simply because we start from a elliptic defined by Calabi-Yau, or because the curve is embedded into T2 times the complex plane. Now, how do we relate this to defects? Well, the intuition is that the four-dimensional Seiberg-Witten curve can be understood as the modular space of co-dimension 2 defects. So it gives you the phase space of this defect. So once we start to quantize the corresponding Seiberg-Witten curve, then we quantize the phase space, and now the corresponding Hamiltonian is acting on an eigenfunction, and that eigenfunction now is the eigenfunction of the co-dimension 2 defect. So that's the partition function, which then in the 6-dimensional setup is going to wrap the T2 and one plane inside the R4. Geometrically, you can also think about the mirror Calabi-Yau picture again, and here we know that the insertion of the co-dimension 2 defect corresponds to the insertion of a brane that wraps the special Lagrangian cycle in the mirror Calabi-Yau, which then intersects the Seiberg-Witten curve precisely at one point. So you're going to be back at the picture that the Seiberg-Witten curve gives you the modular space of this co-dimension 2 defect. So that's sort of the weight picture. Now, in the rest of the time, I would like to just illustrate some of these results in the two cases that we have already been considered. So that's class SK, that's the example I've shown you before, and then I briefly show some results on the E string. So starting with the class SK, here it is more useful to use the M theory or the type 2 brane realization. That means we take now two M5 branes, which are transversed to the A-type singularity, and we chose the 60-volt volume to be T2 times the four-dimensional omega background. And most technical things that we do is we compute a partition function, which decomposes into perturbative and the instanton piece, and the instanton piece can be expressed as a sum over the elliptic general. The setup is essentially in a brane language given by two NS5 branes with the 6 branes suspended in between. So you get the corresponding 6-dimensional gauge theory description on the tensor branch. And then if you want to understand the instanton corrections, we also have to suspend the two branes inside the D6, which give you the instanton corrections. And volt volume theory on the D2s is then summarized in this 2D curvature gauge theory, for which we then compute the elliptic general in order to derive the instanton corrections. But of course, this slide so far does not have any defects. So now we need to wonder, how do we introduce a defect into the theory? And for this, we start with a co-dimension 2 defect, which we can introduce via a modification of the Higgsing procedure that tells you can start from a theory higher, such that you can, for instance, Higgs the SUK plus 1 theory to the SUK theory, plus now being in the presence of a defect. And pictorially, how you do this is in a brane configuration, you start aligning gauge and flavor branes. And now do the modification in the Higgsing process, the brane that you can move along the Higgs branch direction is not just moving away, but actually it leaves behind the D4 brane, which is suspended between the brane that moves away and the residual brane configuration, which gives you then the theory that you would like to study. And this D4 is then wrapping not only the T2, but it's also wrapping one of the planes inside the four-dimensional omega background. And then, of course, you have a new brane, so you're going to have new open string state, which come as modifications to the partition function, which you need to compute. So, for instance, you see this red pieces in the 2D theory, which are the new contributions, which you can straightforwardly compute using the standard technology. But that's not quite what we want to do, because actually what we want to find is how the Seiberg-Witten curve is quantized and how it acts on what is the corresponding eigenfunction. So the corresponding setup that we want to do is we want to find a difference equation which annihilates which acts on the co-dimension 2 defect partition function, but only in a very specific limit, which is called the Nekrasov-Chertashvili limit, telling you that we not have the most generic omega background, but actually we take one epsilon parameter to 0, and the other one we keep finite, which takes the role of the Planck constant. And in this limit, we gonna evaluate normalized defect partition functions. The strategy in order to find this difference equation is essentially we introduce the shift operator, we compute the action of the shift operator on the defect partition function. For this, it's mostly useful to use a path representation. And then at the end of the day, we remember how the original Seiberg-Witten curve has been or can be derived via a saddle point equation. Here we perform the same logic. First of all, we take a path integral representation that tells you you start from the elliptic genera and you sum them all up, just starting all of the elliptic genera. And we do some manipulations such that we get a path integral in two path integral variables. One is sort of a density rho and the other one is an auxiliary lambda. And then within this path integral, we can now perform the NS limit and we get the dominating contribution from the saddle point equations. And these saddle point equations are now used to derive the quantized Seiberg-Witten curve. So roughly in this picture, you get one equation that is satisfied for a certain point, which is the saddle point. You can analyze the properties of this equation. You can find a pole-free configuration, which is given by the ratio on the left-hand side. And then since it's pole-free, it can only be something that is not singular. So there is some quantity P that needs to be determined. Now, the only thing left we need to do is we need to get rid of this omega, because I haven't told you what this omega is, because this omega is just something that pops out in, or that we use in order to do the saddle point analysis. But we can replace the omega by using the action of the shift operator on the defect partition function. And we can see that the omega is equal to the ratio of the shifted partition function divided by the unshifted one. Once you believe that you can do everything as I told you, you can actually write down a difference equation acting on the co-dimension 2 defect partition function. But of course, you still need to figure out what is this object P. And it turns out this object P is another defect, which is called the Wilson surface or a co-dimension 4 defect, which can be again introduced by a different type of brane. You can repeat the same computations of the partition functions, and then an explicit verification tells you that the object P, determined solely from the difference equation, matches precisely the normalized defect partition function of this object. So at the end of the day, you can finally write down your quantum curve. And the quantum curve now is acting on the eigenfunction, which is the normalized co-dimension 2 defect. And we see in comparison to the classical curve that now the exponentiated variable t is now replaced by shift operators. Everything that came from these mu-L terms, which are like flavor fugacities, remains the same. But everything that came from gauge fugacities now has been replaced by the Wilson surface expectation value. And this is sort of the structure that we find. If you then are brave enough and want to consider further six-dimensional SCFTs, you can go to the next example, which for instance is the E-string theory, for which we again have a type 2A brane configuration that allows us to embed the E-string theory in a family of SPK gauge theories, such that we can use a Higgs mechanism in order to go from SP1 with 10 flavors to the E-string theory. And once we have this Higgs mechanism, we know exactly, again as before, how to include a co-dimension 2 defect into this system. And similarly, co-dimension 4 defect can be introduced by another type of brane. And the elliptic genera for this theory have already been worked out in the presence without any defects by various people. And you already see one of the difficulties, because now the elliptic genera, for instance, have to be computed for theories which have an orthogonal gauge group, which is not connected gauge group. So there are a lot of more technical issues that you have to take into account. But following the same logic as before, now everything a bit more involved, you can derive a quantum curve, which follows the same pattern as before. So we have shift operators, which act on the co-dimension 2 defect partition function. Now we've only written it for the instanton part. And you see that there's a shift, and then there's some prefactor with some theta functions. And on the right-hand side, now we see again a Wilson surface expectation value, which is again a co-dimension 4 defect. And comparing to the classical curve, which has been derived for the case where only SO8 cross SO8 symmetry is preserved from the global E8 symmetry, you find that the pattern matches precisely again. So the exponentiated variable is replaced by a shift operator. Everything that sort of comes from the flavors remains the same, but everything else can be interpreted as Wilson surfaces coming from a co-dimension 4 defect. So long story short, what we have found now is that if you want to study the quantization of six-dimensional Seiberg-Witten curves, or you want to understand how certain defects interact among each other, then you see that the quantization of these curves is intimately related to various types of defects, and they play various different roles. We have that the co-dimension 2 defect is precisely the eigenfunction of the corresponding quantum curve, precisely because we have this understanding that the Savoy-Witten curve sort of describes you the moduli or the modular space of the coordination 2 defect. Similarly, the coordination 4 defect appears because you have in the Savoy-Witten curve appearing gauge fugacities, and they are then promoted to Wilson surface defects in the 6-dimensional setting. But now, if you look at this, and if you remember the tremendous developments in the field of Savoy-Witten curves, there are many future directions that you can pursue. On the one hand side, we have the 60 classification of everything that can be realized from F-theory on elliptic fibered color bearer 3. So you can ask what are the quantum curves for the other 60 SCFTs on the other minus n curves, or you can start looking at chains of curves. So you can look at the realm of curve gauge theories and find out how the Savoy-Witten curve looks there. Similarly, we know that the Savoy-Witten solutions are intimately related to integrable models, which has also been generalized to the 5D and 60 setting. Now you can ask what is the relation, and we already know, for instance, in the classes K, that the quantized Savoy-Witten curves is in the elliptic Ruisenhaus-Schneider integrable model, and we also know for the E string that the corresponding quantum curve that we have derived precisely matches with the difference operator from the Van Degen model. But that's so far everything we have done. There's no further analysis that we've done so far. So there are many open questions in various directions. And finally, you can ask a different question. Since you have a coordination 2 defect, what is the mode buoyancy living on that defect? Because it's supposed to be a 4D theory, and you can ask what is the relation of that theory compared to the 6-dimensional theory. But with this, I would like to thank you for the attention. And if you have any questions, let me know.
Thank you very much. So if you have a question, you can turn on your microphone and ask questions.
I have a question.
Yeah.
In the case of the 4D n equals 2 theory, we think of the Savoy-Witten integral systems. And here you're talking about elliptic uplift because we have the 61,0 theory on R4 plus feature.
Yes.
Is there still a notion of phase space? So the phase space was a well-defined notion, the Coulomb branch of the 4D n equals 2 theory. But here, how should I think of this elliptic uplift integral system in the phase space?
Oh, that part I haven't studied. I'm fairly new to this integral model side, so that's something certainly to be answered.
Any other questions?
In this program, codimension 3 top operator doesn't play any role?
No. Yeah, we haven't seen any appearance of any such operator. But also, we haven't been looking at it. That's also honestly to be said.
Other questions? So let me ask one question. So if we were talking about the not one E string but 2 n E string, so is also corresponding differential equation known, or is that
An E string? You would just take the SP theories.
yeah? We don't want to.
Yeah, you can write them down.
So corresponding integral system is also known.
For this integral system side, I don't know too much. The difference equation you can probably write down. Not sure it's very explicit anywhere, but you can probably look at that. That's certainly doable. Right.
Okay, thank you. Any other questions? Okay. If not, let's thank all the speakers in these sessions. So we can close this parallel session today. Thank you very much for coming.